Electric potential energy due to a uniform electric field. Up until now, we've dealt with electric fields, potential energies, and potentials due to individual charges. Next, let's analyze situations with uniform electric fields. A uniform electric field is created by two infinite planes of charge that are separated by a small distance. This will be derived eventually in AP Physics C. The planes have equal amounts of charge, with one plate being charged positively, like this plate on top here, and the other negatively. Two infinite planes are approximated by two parallel plates, where the distance between the plates is much smaller than the plate dimensions, so this is not to scale. A real to scale version would look more like, here's one plate, there's another plate. They'd be very close together compared to how long they were. And the electric field between the plates is uniform. It will have the same magnitude and direction everywhere between the plates. And the electric field outside the plates is zero. This is an idealized picture of a critical electric circuit element, the capacitor. Real capacitors have a much smaller distance between their plates, but the expanded view is shown for clarity. We're now going to work with electric field, electric potential energy, and electric potential to explain the theory of the capacitor. For the parallel plates, the electric field is generated by the separation of charge, with the field lines originating on the positive charges and terminating on the negative charges. The difference in electric potential is responsible for the electric field. When an external force pushes a charge in the direction it wouldn't naturally go, the potential energy in the plate charge system increases. In the picture, a positive charge is being pushed up towards the positive plate. Positive work needs to be done by an external force to move the charge in this direction. Since the positive charge is moving opposite the electric field, negative work is being done by the electric field. If a positive charge was placed within the field and then released, it would move from top to bottom, the direction it naturally wants to go, since it's repelled by the positive charges up here and attracted to the negative charges down here. In this case, the work done by the electric field would be positive, since the electric force is in the same direction as the charge's displacement. The potential energy of the system would decrease, while the kinetic energy would increase. This is directly analogous to the movement of a mass within a gravitational field. If you drop a ball, it speeds up as it falls. If there are no other forces present, the charge would accelerate to the bottom with an acceleration determined by Newton's second law. Acceleration equals net force divided by mass. However, if we want the charge to move with a constant velocity, then an external force must act opposite to the electric field. This external force would need to be directed upwards. Since the charge is moving downwards, the work done by the external force would be negative, while the work done by the electric field would be positive. In summary, applying an external force so that this positive charge would move downwards at a constant velocity would require that the work done by the external force is negative, since the displacement is down, but this force is up. The work done by the electric field would be positive. The net force, and therefore the net work, is zero, so there would be no change in kinetic energy. And the potential energy of the plate charge system decreases because this charge is moving in the direction it wants to go. If we look at an energy bar chart for this scenario, the charge starts out with potential energy. It's at rest. And then it is lowered. So what's happening is that this external force is doing negative work. It's removing energy from the system. And at the end, when the charge is down where it wants to be, there's no more energy. There's no more potential energy, and there's no change in kinetic energy. To move a positive charge from the bottom to the top plate, an external force must act upwards in opposition to the electric field. The work done by the electric field is negative, since the field points down but the displacement is up. The potential energy of the system will increase, directly analogous to the movement of a mass within a gravitational field. If you lift a ball up away from Earth, it gains gravitational potential energy. If you want this charge to move with constant velocity, then these forces need to be opposite and equal. The external force must have the same magnitude as the electric force down, but it needs to act in the opposite direction. Since the charge is moving upwards, the work done by the external force is positive, while the work done by the electric field is negative. In summary, applying an external force so that a positive charge moves upwards towards a positive plate at a constant velocity would involve positive work being done by the external force, negative work being done by the electric field, the net work being zero, and therefore there's no change in kinetic energy, and since we're pushing this charge in the direction it does not want to go, the potential energy of the system increases. In this case, we start out with no energy, and then the external force does positive work on this charge, leaving us with potential energy at the end. Similar logic works for a negative charge. However, the directions of the electric force and the external force are reversed, which will change their signs, as summarized on the next slide. In this case, we can read this free body diagram and determine what's happening. This negative charge wants to move up to the top. Now we're going to be applying an opposite external force so that it moves at a constant velocity. Alright, so let's analyze this situation. The electric force is pushing the charge upwards. Therefore, the work that force is doing is positive since it's in the same direction as displacement. Therefore, the external force is keeping it back so that it's not accelerating. That's doing negative work. If we look at the energy bar chart, while this negative charge is close to the negative plate, there's potential energy in the system. But then, this external force is removing energy from the system. Therefore, we end up with no energy. Let's determine what's happening here. So, this charge is being brought down, this negative charge is being brought down to the negative plate. So that's moving in the direction it does not want to go. That means it must be being pushed by an external force, which is doing positive work since that's the direction the charge is moving. The electric field is trying to push the charge the other way, so it's doing negative work. We start out with no energy when the charge is at rest by the positive plate. But then this external force does positive work, increasing the energy of the system, and it's stored as potential energy.